Hi everyone, my name is Mohammad Yassin and I am from the Department of Digital Anti-Aging Healthcare at NJ University. Today I am thrilled to present our research on deep learning based cervical spine bone detection, a case study using YOLO. The core of our investigation revolves around the groundbreaking application of deep learning techniques, specifically leveraging the YOLO for the precise detection of cervical spine bones. This case study investigates YOLO effectiveness in identifying these critical anatomical structures in medical images, detection of spine bones using YOLO. So next slide. Here is the content of presentation. The presentation will commence with an introduction providing an overview of the topic. Following that, we will take a look at the data set and its description, outlining key aspect of its original and composition. Subsequently, we will explore the data pre-processing steps undertaken to prepare our data set. Moving on, we will focus on YOLO V5, the chosen deep learning model, and discuss its implementation in our study. Finally, we will conclude by presenting the result and engaging in a discussion of our finding. Next. In this slide, we introduce the detail of the cervical spine, which constitutes the uppermost section of spine, comprising 7 vertebra level as a C1 through C7. These structures play a vital role in supporting the head and neck. Beyond its structural significance, the cervical spine holds a pivotal responsibility in facilitating the flexibility and range of motion necessary for the movement of our head in various directions. The significance of the cervical spine becomes evident when considering that injuries or certain medical conditions affecting it can lead to symptoms such as pain, numbness, or weakness in the neck, arms, or hands. Next, significance of detecting cervical spine bones in medical applications. We underscore the critical role of accurate detection in diagnosing and treating injuries and medical condition affecting this region. In the realm of medical application, the detection of cervical spine bones proves indispensable for assessing traumatic injuries like fractures or dislocations. Moreover, its precision holds immense importance in the planning and execution of surgical procedures, particularly in the context of cervical spine surgery. Beyond treatment, the accurate detection of cervical spine contribution significantly to a medical education, enhancing the understanding of the cervical spine structures and function for students and healthcare professionals alike. Next, turning our attention to the need for accurate and efficient cervical spine bone detection method, we emphasize the critical importance of precise detection method in ensuring timely and appropriate treatment while minimizing the risk of complication. Delays or misdiagnosis can lead to inadequate treatment, prolonged recovery times, and even irreversible neurological damage. Traditional methods such as visual inspection of radiographic images by human experts are not only time consuming but also susceptible to human error. Uh, Recognizing these challenges, deep learning based methods emerges as a promising solution. These methods have the potential to significantly enhance the speed and accuracy of cervical spine bone detection, enabling earlier diagnosis and treatment. By leveraging advanced technologies, we aim to address the press, um, pressing need for efficient detection methods that can positively impact patient outcomes and overall healthcare quality. Next, moving on to our dataset, which forms the backbone of study. The data utilized in this research is sourced from the RSNA 2022 cervical spine fracture detection competition hosted on Kaggle. Within this dataset, three main folders hold invaluable information, such as train images, bounding box, and segmentation are these files. Each folder is dedicated to specific patient containing multiple slice images pertinent to the corresponding case. This comprehensive dataset serves as the foundation for training and evaluating our model, providing a diverse range of medical images for a thorough investigation into cervical spine bone detection. So, next, data set description. Now let's get into the specifics of our datasets. With a focus on the dataset description field, the segmentation file within our dataset proves instrumental, providing label information for each vertebra in the cervical spine from like C1, C2, C3 and C7. This segmentation allows for the precise anatomical identification of each vertebra. In this segmentation marks unique values plays a key role in indicating the presence of specific bones for each slice. For instance, in our example here, that sample image from segmentation file. In our example, we have unique values 0 and 6 here. 0 represents the background and specifically denotes bones C6, and C6 denotes the bone 6. C6 means. This specific level of labeling not only speeds up model training but also ensure accurate and detailed identification of cervical spine bones throughout the dataset. Next slide, data pre-processing. Now let's look at the details of our data pre-processing phase. The first step involves extracting and carefully analyzing DICOM files to identify the slice that corresponded to the relevant vertebral regions. Next, based on the segmentation marks, bounding boxes were skillfully generated to encapsulate the identified bones within each slice. To seamlessly integrate this information into the YOLO V5 framework, the bounding box coordinates were extracted and thoughtfully saved in TXT file, ensuring compatibility with the YOLO V5 model. Additionally, for enhanced efficiency in model feeding, the corresponding DICOM image underwent conversions to the PNG format. This comprehensive data preprocessing pipelines lays the foundation for accurate and effective utilization of dataset in training the YOLO V5 model for cervical spine bone detection. Next, YOLO V5. Now let's explore the cornerstone of our methodology, YOLO V5. YOLO V5, which stands for You Only Look Once version 5, is an open source object detection framework uniquely designed for real-time scenarios. YOLO V5 provides a compelling blend of speed and accuracy, making it versatile for a wide range of applications. This framework introduces a streamlined architecture marked by enhanced performance when compared to its predecessors, solidify its status as a popular choice for computer vision tasks. YOLO V5 lies in its commitment to simplicity, efficiency, and state-of-the-art performance. Within the machine learning and computer vision communities, As we integrate YOLO V5 into our study, its capabilities become instrumental in achieving precise and efficient cervical spine bone detection. Next, now let's into the detail of our training YOLO V5 phase. Our dataset comprises a total of 9,170 images that was divided into 7,336 for training and 1,834 for validation. These images represent the anatomical regions corresponding to the vertebra C1, C2, and so on, C7. And here in the table we can see that following experimental parameters such as epochs 200, MS size 512, learning rate, base size, optimizer, momentum, like so on. These carefully chosen parameters aim to optimize the YOLO V5 model, ensuring effective learning and accurate detection of cervical spine bones. As we progress through the training phase, this setting play a crucial role in fine-tuning the model for our specific application. Next, result and discussion. In our exploration, all four versions of YOLO V5, including YOLO V5S means YOLO V5 small, medium, YOLO V5 large, and YOLO V5X were rigorously employed. Through a careful comparative analysis, the finding illuminated distinct performance superiority of YOLO V5X over its counterparts. The precision, efficiency, and overall effectiveness of YOLO V5X in our specific application surpassed that of other models, underscoring its significance in achieving superior result for cervical spine bone detection. Next, here is the accuracy and loss graph to gain deeper insight into our model performance metrics. These graphs showcases the box loss and object loss for both the training and validation phases, providing a visual representation of the learning dynamics. Additionally, we will examine key metrics including precision, recall, specifically for YOLO V5X. These metrics offer comprehensive evaluation of the model accuracy, sensitivity, and performance various threshold. Next, this is the confusion matrix, turning our attention to the confusion matrix of YOLO V5X. This figure provides a comprehensive visual representation of the model performance on our validation dataset. The confusion matrix offers a detailed breakdown showcasing the accuracy of detecting cervical spine bones C1, C2, C3, C4, and C7. This analytical tool allows us to examine not only the correct classification but also instances of misclassification, aiding in the identification of potential areas for improvement. So next, our output of YOLO V5. In this figure, our model effectiveness in detecting cervical spine is vividly illustrated. The results showcase the remarkable accuracy of our system, with specific instances highlighted. In this image, in this figure, we can see that C3 detected with the confidence of 90%, and C5 detected with confidence of 80%, like C6 with 90 and C7 with also 90. This visual representation serves as a testament to the robustness and precision of our YOLO V5 model is in successfully identifying individual cervical spine bones. reinforcing the efficacy of our approach in cervical spine bone detection. Next, conclusion. As we arrive at the conclusion of our study, it is evident that cervical spine bone detection holds paramount significance in diverse medical applications ranging from diagnosis to surgical planning and treatment assessment. Throughout our exploration, we harness the power of YOLO algorithm for the precise detection of cervical spine structure. Utilizing four distinct YOLO V5 architecture, our comparative analysis revealed the outstanding performance of YOLO V5X. This particular model demonstrates exceptional accuracy in identifying cervical spine bones. As we conclude our presentation, I extend my sincere gratitude for your time and attention. Thank you for joining us on this exploration of deep learning based cervical spine bone detection. If you have any question or insight, I would be glad to address them. Thank you once again for being a part of this discussion.